there. Welcome back. I hope you had a good spring break. I'm sure it was different from what you're used to, but I hope it was good nonetheless. We're moving into fourth quarter, and the topic of fourth quarter is waves. So we'll talk about sound waves, light waves, water waves, all sorts of waves. But before we get into waves, we need to do a little groundwork and learn about simple harmonic motion. So, one example that you already have seen of simple harmonic motion. I don't know if you remember the pendulum lab we did first semester, but we looked at the repetitive motion of back and forth, and that's characteristic of simple harmonic motion. Another example would be a mass by spring. In this case, the mass is down, up and down. But you see that same repetitive motion of the pendulum back and forth over the same path. So, what are some of the characteristics of, well, some definitions actually that we need for simple harmonic motion? We said it was a repetitive motion, but here are some special vocabulary terms you need. A cycle is one complete vibration. So imagine that you let go of the pendulum. It's from the time you release it to the pendulum swings through all the other positions and back to its starting position. That would be a cycle. The period, if you remember, we measured the period of a pendulum in the lab that we did. That's the time for one complete cycle, and it's measured in seconds. Frequency is similar to period, although it's the inverse, really. It's the number of cycles every second. In other words, how many cycles in a second instead of how many seconds in a cycle. The units for frequency are cycles per second or hertz, and a hertz is simply 1 cycle per second. And so, as I mentioned, and as you can probably notice, period and frequency are inverses of each other. If you know that the period of a pendulum is 10 seconds, then the frequency would be 0.1 cycles per second. The equilibrium position is just what it sounds like. When the pendulum is hanging and it's not swinging, that's where it's in its equilibrium position, when all the forces on it are balanced. For the mass spring vibrator, the equilibrium position would be whatever position it's in, again, when it's not vibrating back and forth. So it's generally in the center of its vibrational path. And the amplitude is a measure of the distance, the displacement from the equilibrium position to the maximum displacement position of the object, whether it's the pendulum or the mass at the end of the spring. So let's take a look at an example here. This one's not going to move for you, but if you imagine this mass on the end of the spring vibrating up and down, this is the equilibrium position, the position it has or it's in when it's at rest and not going through its vibrations. If it vibrates back and forth between this high position and this low position, then the distance here from equilibrium to amplitude is the amplitude, a measure of the amplitude, and this would be the amplitude on the other side. So the mass vibrates through that whole distance in one complete cycle. And what's interesting, what you see here, is if you plot the position of the mass as a function of time, we end up with this sine wave, and that it gives you a little bit of an idea of the connection that we have between simple harmonic motion and waves. So, let's try a problem. You can read it for yourself, but basically we time a pendulum and it goes back to its starting position 5 times during the 10 seconds that it's been swinging after it's been released from rest. And when it swings, it goes 8 centimeters from its release point to the amplitude position on the other side before swinging back. So, first question, calculate the period of the pendulum. So I'm going to give you a moment to do that. Here's the numbers that you see there. Okay, and hopefully you came up with the same thing I did. If it was 10 seconds for 5 vibrations or 5 cycles, the period would be 2 seconds. Try this one. What's the frequency of the pendulum? Okay, again, hopefully you came up with either 5 cycles divided by 10 seconds, which gives you a half a hertz, or maybe you look back at the period and said, hey, I know frequency is 1 over period, so the frequency must be a half a hertz. And last but not least, what's the amplitude of the pendulum swing? Read carefully, because you really have to discern here what is amplitude and what is not. And hopefully you came up with the fact that, okay, if it swings from its release point 8 centimeters to the opposite amplitude position, then the amplitude is actually only 4 centimeters. That's it. Pretty basic. Your homework for tonight will be to try some more problems similar to this. So obviously we're just warming up, getting into the quarter in a nice gradual way.